Water boils when it is heated, but water can also boil at room temperature. In this glass venturi, water is flowing from left to right. According to Bernoulli's integral, where the velocity is increased, the pressure is decreased. When we increase the flow rate, the water in the throat, where the pressure is lowest, begins to boil. Small bubbles are formed. These are cavities filled with cold steam and other gases diffused from the liquid. The noise is generated by the collapse of these bubbles as they move into the higher pressure in the diffuser. Water is flowing past this propeller model at constant speed and pressure. Let's increase the RPM of the propeller continuously. Bubbles form in the regions of lowest pressure in the flow. To visualize the flow more clearly, we look at it under stroboscopic lighting, so that to the eye, the rotation appears almost stopped. About 100 years ago, when propellers began to replace paddle wheels on ships, it was discovered that such cavities produce a great waste of power. These cavities on the propeller, the bubbles in the beaker, and in the venturi throat are all examples of cavitation. Generally, we refer to cavitation as the process of boiling in a liquid as a result of pressure reduction, rather than by external heat addition. However, the basic physical and thermodynamic processes are the same in both cases. In this film, we will see the various forms of cavitation, illustrate some of the consequences of cavitation in engineering applications, and examine the physical factors involved in the process of inception and development of cavitating flows. First, let's look at some different types of cavitation. We will work in this circulating water channel. Here we can vary water speed and temperature and absolute pressure independently of each other. This hydrofoil is set at an angle of attack to lift upward. With this thick, symmetrical hydrofoil, we can illustrate a number of effects on a single model. The ambient pressure is well below atmospheric and held constant. The flow speed is being increased at a uniform rate. Air bubbles have been introduced to help visualize the motion. Cavitation occurs first at the intersection of the hydrofoil and the strut. This happens because the presence of the strut causes a greater pressure reduction at this intersection than elsewhere on the foil. But we will confine our attention to the foil section away from the influence of the strut. At low speed, cavitation on the foil itself first occurs in the low-pressure core of the laminar boundary layer separation region associated with low Reynolds number. At higher speed, and thus larger Reynolds number, the appearance of the cavitational flow changes. Transition from laminar to turbulent boundary layer has occurred. Laminar separation has been suppressed, and cavitation now begins near the minimum pressure point close to the leading edge. We have been looking at the cavitation under incandescent lighting. Under stroboscopic lighting, we see that the cavitating region is again made up of individual bubbles. The apparent dancing is only a consequence of the strobe lighting. Actually, each flash of the strobe reveals different bubbles in different locations as they travel downstream. With high-speed photography, we can follow the history of the same bubble as it is swept downstream. Each bubble grows as long as it is in the low-pressure region of the foil. The bubbles collapse when they enter the higher pressure region near the trailing edge. Individual bubble cavitation is characteristic of forms with gentle pressure gradients, such as those on this foil with a well-rounded leading edge. When the leading edge is sharp, however, cavitation begins at this edge. This type of cavitation maintains itself as a continuous vapor-filled cavity, rather than a mass of small individual bubbles. Its size depends on the angle of attack, the ambient pressure, and the flow speed. The cavity grows when the angle of attack is increased. It also grows when the ambient pressure is reduced. We are lowering the pressure by dropping the water level above the foil by means of an upstream sluice gate. The cavity also grows when the water speed is increased. When the cavitating region extends beyond the trailing edge of the hydrofoil, we call the flow a supercavitating flow. The supercavitating, sharp-edged foil is a type used on very high-speed hydrofoil boats, such as this 80-knot boat. Hydrofoils designed for non-cavitating or subcavitating operation are used on hydrofoil boats at speeds below about 50 knots. Let's look at the propeller model again. At this point, we want to emphasize the role of the ambient pressure. The pressure is low and the propeller RPM is constant. Notice the cavitation on the blade faces as well as in the tip vortices. The pressure is now being increased by raising the pressure of the gas above the water surface. The cavitation is reduced, and now it is almost suppressed. Incidentally, this procedure simulates the behavior of a cavitating submarine propeller as the submarine dives from a level near the ocean's surface. This model is typical of a propellation. Here is a propeller designed to perform well at very high speed, where cavitation is unavoidable. This type of propeller operates under supercavitating conditions. Under stroboscopic lighting, we can see that the cavities spring from the leading edge and envelop the entire blade, as in the case of our supercavitating hydrofoil. Cavitation may also occur in hydraulic machinery, such as pumps and turbines. Here is cavitation on the blades of an inducer pump model seen with strobe lighting. Cavitation can also occur in turbulent shear flows because of the local pressure reductions in intense turbulent eddies. For example, let's look at the flow behind this circular disc. As the flow speed is increased, the pressure fluctuations in the zone of high turbulent shear lead to cavitation. With further increase in speed, the entire wake appears to be filled with vapor bubbles. Eventually, the flow becomes a true cavity flow, as distinguished from a cavitating turbulent wake. With high-speed photography, we can see more of the details of this complex flow. The flow at the end of the cavity re-enters and moves upstream. This re-entrant flow is illustrated more clearly in the cavity trailing our supercavitating hydrofoil. Re-entrant flow is characteristic of such cavity flows. The momentum flux in the reentrant jet is equal to the pressure drag of the body. The jet kinetic energy is dissipated. Another type of cavity flow occurs when a missile enters water at high speed. In this sequence, a steel ball is shot into a tank of water. Here, the camera is turned so that the water surface appears to be vertical and the missile to travel horizontally. The cavity follows the missile into the water and eventually closes off, producing reentrant jets which are seen here in slow motion. Initially, the gas within the cavity attached to the missile is air rather than vapor. Progressively, the air is left behind, and if the motion persists long enough, the cavity content will be vapor primarily. Still another example of cavitation occurs in the type of bubble chamber used for studies of high-energy nuclear particles. In this photograph, a positron-electron pair has produced a track of bubbles in liquid hydrogen, which is at a pressure below the boiling point and is therefore unstable. We have seen that cavitation can take several forms: small transient bubbles, large, more or less steady cavities, non-stationary cavities, and often a mixture of these types. Let's turn now to an examination of some of the effects associated with cavitation and cavitating flows. What happens to a machine when it begins to cavitate, and how does performance vary with increasing extent of cavitation? Since hydrofoil sections make up so many different types of machines, pumps, turbines, propellers, propeller shaft struts, mixers, we can illustrate what happens to all such machines by studying the forces on the hydrofoil section itself. We have suspended the first hydrofoil model from force gauges, which show us lift and drag on these scales. The flow speed is constant, and the gauges register the corresponding lift and drag. The ambient pressure is set at a level well above that at which cavitation can occur. We are going to induce cavitation by decreasing the ambient pressure in the test section, keeping the speed constant. At first, there is no appreciable change in either force. As cavitation develops, lift decreases and drag rises. You can see from the force balances that the flow is quite unsteady. When we lower the pressure further and allow cavitation to spread, the lift decreases further and the drag continues to rise. We can get an idea of what has happened by examining the pressure distribution on a hydrofoil section. This curve represents the pressure on the upper surface, and this one, the pressure on the lower surface, before cavitation begins. The lift is proportional to the difference in the areas under the two curves. As the ambient pressure decreases by a certain amount, the pressures on the upper and lower surface decrease by exactly the same amount, at least until the upper surface begins to cavitate. At this point, the upper surface pressure can no longer decrease below the cavity pressure, which is near the vapor pressure. Since the pressure on the lower surface does decrease, the lift drops. Actually, as cavitation develops, the shape of the pressure distribution changes somewhat. The resultant pressure distribution is such as to cause an increase in drag. Thus, hydrofoils, and for the same reasons, many hydraulic machines, which are designed for efficient subcavitating operation, lose efficiency when cavitating. Where cavitation is unavoidable, and conditions are such that supercavitating flow can be assured, it is possible to use supercavitating hydrofoil profiles specifically designed to achieve high lift-drag ratios. Another important effect is the noise that collapsing cavitation bubbles produce. A partial vacuum has been pulled in this space above the water column. As I accelerate the tube downwards, the inertial forces produce a pressure gradient in which the pressure decreases as you go down from the free surface. At some level, the pressure is low enough for the liquid to cavitate. The noise is a result of shock waves generated upon bubble collapse. The pressures associated with collapse are high enough to cause failure of metals. Here is cavitation damage on the runner of a large hydraulic turbine, which operated under cavitating conditions for an extended period of time. This propeller operated under cavitating conditions for only a few days. Similar damage can be produced on pump parts, such as this impeller of a pump for high-temperature liquid sodium, and in the low-pressure regions of hydraulic structures, such as this large power dam spillway tunnel. There has even been speculation that brain damage can be produced by the collapse of bubbles in the cranial fluid when the skull is accelerated under the action of a sharp blow. To show you how quickly cavitation can cause damage, we will expose the surface of this aluminum button to a cavitating cloud. The cavitation will be produced in an alternating pressure field created by oscillating the specimen itself. The specimen is driven by this magnetostriction oscillator. We are looking directly upward at the face of the specimen. The total amplitude of vertical oscillation is only 0.02 of an inch, but the pressure is changed from below vapor pressure, as the button is accelerating upward, to a high pressure, as it is accelerating downward, at the rate of 14,000 cycles per second. After 1 minute, the highly polished surface has been eroded, and significant weight loss has already occurred. Here is a side view of this experiment. The high collapse pressures and the mixing caused by ultrasonic cavitation is put to good use in industry. For example, for accelerating chemical reactions, industrial cleaning, and homogenization of milk. Let's now look more closely at the motions of the small transient bubbles which cause so much trouble. These bubbles have a life history measured in milliseconds. They grow during their passage through the low pressure region and then collapse as they enter the region of increased pressure. If the bubbles have a relatively large initial gas content, they will collapse and then rebound, as in these high-speed photographs taken by Knapp and Hollander some years ago. These bubbles were formed in the low-pressure region near a body of revolution. Only a small portion of the flow field is shown. These bubbles were formed in the interior of a water sample subjected to an alternating pressure field. If such cavitation bubbles remain spherical throughout their life history, extremely high pressures would be developed upon collapse when the bubble is almost microscopic in size. Estimates indicate the pressure produced near the position of minimum radius is of the order of thousands of atmospheres. However, the bubbles become unstable during their motion and do not maintain a spherical shape. These photographs, taken by A.T. Ellis, show how distortion may proceed. Such deformations tend to reduce the velocity of the bubble wall and consequently the pressures that are developed. If the bubble collapses in an unsymmetrical pressure field, as in this experiment with a bubble at a wall, an internal jet is formed, much as in the case of the missile entry cavity. The velocity of the jet is very high. The impact of these jets on a surface can produce high stresses. Here, a bubble collapses near a photoelastic specimen. The close spacing of the fringes indicates the very high stresses that are induced. Clearly, jet impact is another mechanism which may account for severe damage. There is an important parameter which describes the conditions for cavitation similarity and is the basis for scaling of cavitation phenomena and model experiments. This is the cavitation number sigma. P sub A is the ambient absolute pressure, P sub C is the cavity pressure, rho is the mass density of the liquid, and U is a reference speed characteristic of the flow. The cavitation number at which inception of cavitation takes place is called the critical cavitation number. Above the critical cavitation number, no cavitation occurs. Below the critical, it does occur. Operation with a cavitation number well below the critical produces a very large cavitated region. In two-phase, one-component flow, the cavity pressure is just the vapor pressure. In a multi-component flow, the cavity pressure is the sum of the partial pressures of the vapor of the liquid and of any gases that may have been introduced into the cavity. In fact, a cavity developed entirely with gas from an outside source behaves and appears very much like a cavity formed by means of the vaporization process we have been discussing. To illustrate this point, we will compare this vapor cavity with an air-filled cavity. Air at near atmospheric pressure is being introduced through the sting into the wake of the disk. Its envelope looks very much like the vapor cavity we have just seen. We formed this air cavity, or ventilated cavity as it is called, by operating the channel at a low water speed and high ambient pressure. To form the vapor cavity, the channel was operated at a much higher speed and under considerably lower pressure to obtain approximately the same cavitation number. The size of the physical system being studied does not appear in the cavitation number, but it is a factor in the Reynolds number. Consequently, as long as Reynolds number effects are taken into account properly, cavitation similarity requires only that the cavitation number be the same for the prototype and for the model. We see that a model experiment can be made at lower speed than that at which the prototype operates if we simultaneously reduce the pressure under which the model is operated. The operation of the cavitation tunnel is based on this principle. We have seen what cavitation looks like, have learned about some of its effects, and examined some of its features as it develops. Pressures near the vapor pressure requires the presence of nuclei, which contain minute amounts of vapor, gas, or both. Cavitation will occur only when these nuclei become unstable and grow when subjected to a pressure reduction. The conditions for such growth can be derived from an analysis of the static equilibrium conditions for a spherical nucleus. The internal forces produced by the partial pressures of the gas and vapor within the nucleus must be balanced by the ambient pressure and the surface tension pressure at the nucleus-water interface. Thus, the condition for static equilibrium is that the ambient pressure plus the surface tension pressure equal the vapor pressure plus the gas pressure. We've plotted this equation for a nucleus with a particular gas content. The pressure adjacent to the bubble has a minimum value which is below the vapor pressure of the liquid. As long as the ambient pressure is above this minimum and the initial bubble radius is smaller than the radius associated with it, the nucleus is stable and tends to reach an equilibrium radius along this portion of the curve. If, however, the pressure drops below the critical value, the bubble becomes unstable and grows without bound. If a smaller gas content is available, even lower pressures are required. Now let's look at an experiment performed by Ellis to illustrate this behavior. We are looking just below the water surface in a tube which has been evacuated to near vapor pressure. Near the bottom of the tube, out of sight, small nuclei of the order of 5/1000ths of an inch are formed by evolving hydrogen from one platinum wire and oxygen from a second wire by means of an electrical impulse generator. The bubbles are unequal in size, the hydrogen bubble being the larger. As they rise toward the free surface into regions of lower hydrostatic pressure, the larger hydrogen bubble reaches critical size and grows explosively, while the other does not. Although the smaller oxygen bubbles expanded as the pressure was reduced, they never reached a size large enough to become unstable. On the other hand, some of the larger hydrogen bubbles, which moved along a curve such as this one corresponding to a larger gas content, did expand to a size large enough to slip into the unstable region and grew explosively. Bubbles represented by the portion of the curve to the right of the minimum point are already unstable and cannot exist unless stabilized by some external mechanism. Now, even a stable nucleus can decrease in size and eventually disappear because its gas content may diffuse into the surrounding fluid. We can show this with the Venturi experiment by comparing the cavitation inception pressure for freshly drawn water with that for water which has rested undisturbed for some time. Because the discharge is to the atmosphere, increasing the driving head increases the velocity and thereby reduces the static pressure at the throat. This bucket is freshly filled with tap water. As we raise the bucket, cavitation begins at a head of about 2 feet and continues to develop as the head is further increased. We will now leave the water undisturbed for an hour, then repeat the experiment. As we start the flow again, there is no cavitation at the 2-foot head. With the settled water, a much higher head is needed for inception of cavitation, about 3 feet. During the settling period, some nuclei could rise to the surface and vent if they were very large, and some could decrease in size by diffusion of air into the surrounding water. Consequently, a greater pressure reduction was required to cause cavitation in that sample. What we have just seen leads to a dilemma. Nuclei in mechanical equilibrium disappear through diffusion of the gas into the surrounding liquid. Unstable nuclei cannot persist. Yet we have seen that nuclei must be present for cavitation to occur at pressures near vapor pressure. How then can we account for the persistence of nuclei? We must conclude that some external mechanism is required, such as entrapment of gas in the crevices of solid boundaries or on dust particles which contaminate the liquid. We do not fully understand all of the mechanisms of nucleation, and yet such understanding is very important to the prediction of performance either a priori or from models. Many basic aspects still remain to be explained. Nevertheless, we do know a great deal about cavitation, and its effects on performance of machines can be predicted fairly well. when cavitation is unwanted, when it is inevitable, and when it is sought.